Okay, calculus students, today we're going to talk about the extreme value theorem, but before we do so, we've got to get down some necessary vocabulary. Otherwise, it's going to be like I'm talking Swahili to you as we go through an extreme value theorem problem. So just two quick examples here before we get into the nuts and bolts of our discussion. So the extreme value theorem says that if f is continuous on a closed interval between a and b, then guaranteed f has a global maximum and a global minimum on that interval. Not an earth-shattering scenario, but one you've got to keep in mind. So here's a graph. It says below is the graph of some function f of x. Identify all of the relative extrema and absolute extrema of the function. So the words relative and absolute, another word for relative is local. You'll hear that in calculus problems. Relative and local will be used synonymously. As well, extrema and global. Extrema and global. Think of extreme when you hear extrema. Extrema is just a plural form of extreme. So that you understand that. So we know here f is continuous on the closed interval from -4 to 5. I could take my pencil, put it on that red function, and although it's got some sharp points, that's not bothering me. That would cause it to be not differentiable, but it is continuous. So I know this red function is indeed continuous on the closed interval from -4 to 5. Now, critical points is another vocabulary term that you're going to hear serious frequently in calculus class. And you've got to know and be able to snap out the definition of what a critical point is immediately. So critical points are x values where f prime equals 0 or f prime does not exist. I know f prime equals 0 at tops of mountains or bottom of valleys. I know that f prime does not exist at sharp points or points of discontinuity, which are really excluded here after all the functions got to be continuous, or locations where the slope of the tangent line becomes vertical. Okay? Truthfully, I'm looking for critical points, values where f prime is 0, tops of mountains, bottom of valleys, or f prime does not exist. Sharp points are usually the ones you see with scenarios like the one we're looking at. So the global or absolute minimum and maximum will exist at the interval edge. I'm talking right at -4 or right at x equals 5, or at critical points. So if you just shake your brain and look at that graph and I ask you, well, what's the global max? Oh, it's the highest point. You're right, it's the highest point. But what we're saying here is the highest point will exist either at critical points, which it does in this case, or at the end point of an interval. Got to know that for the extreme value theorem. Those will be candidates when we talk later. Okay, so we have the same graph here. See if you can identify all the relative extrema and absolute extrema of the function. So right here, that sharp point, we have x equals -1. That's a relative extrema. The next one, we talk about x equals 2. There's another sharp point there. We've got a relative minimum there. X equals 4, that top of the mountain, you know that's a global maximum and a local maxima. So you can have several local extrema, but only one. Well, you can have a tie game for a global maximum as well. But this guy is definitely the winner when you talk about what's the global max. The highest point on the graph, definitely at x equals 4. What about these endpoints of the interval? You were bragging about those earlier. Well, global extrema are the very highest or lowest points on the graph. And remember, endpoints of intervals can't be critical points. So what we have here are global extrema may occur at the endpoints or on the interior, of the graph's interval. Okay, so when you go to test potentials for global extrema, you've got to test all critical points as well as the endpoints of the interval. Always must test the endpoints of that closed interval when you're going to do a problem like this, okay? Super serious, important. Local extrema can only occur on the interior of the graph. You cannot have a local extrema at the endpoint of the interval. A global max or min, possible. But the local extrema are only available on the interior of the graph. So x equals -4 and x equals 5 are not local or global extrema in this particular example. It's good we're considering those for potential global extrema, but never for local. So there's some vocabulary that probably you didn't have in your backpack before we started today. So see if you guys can do this one. Same kind of challenge. We got to identify all relative extrema and absolute extrema of this function. So I'm looking at tops of mountains, bottom of valleys, endpoints of interval. See how we do here. How about x equals 6? What do you think? X equals 6, I agree, is definitely the global maximum right there. It's not the y value I'm concerned about. That looks like it might be 8 units high. It's the x value location that I'm concerned about, where x equals 6. X equals 9 is the global minimum. Ooh, that's not a bottom of the valley. That's kind of weird. Yeah, that's the end point of the interval. Remember, global max and mins can occur at the end point of the interval. Right there. Okay? So make sure you test and contemplate those. X equals 1 and x equals 6. Check it out, 1 and 6. Those are both local maxima. No surprise to you guys at all, both tops of mountains. What am I going to write next? Do you know? That's exactly right. X equals -2 and x equals +2 are indeed both local minima. They are both bottom of valleys. Okay, so we've really taken care of everything here. We've got the global max and min, and we've identified local maxima, local minima. And we know that the local maximum and minimum cannot exist at the endpoints of the interval, but guaranteed the endpoints of the interval are counted in the competition for the global max and min winner. Okay? So that's kind of the vocabulary you have to take with you here. Take that with you on the next example. Example 3 here will actually give us an extreme value theorem challenge. Take a look at that immediately. Over and out.